Hello, my name is Trifon Kekes, a PhD student in the School of Chemical Engineering of the National Technical University of Athens, and I am going to present you today our joint research with Université Laval entitled Utilization of Delta Manganese Dioxide for the Removal of Indigo Carmine from Aqueous Solutions. Water can be characterized as an eccentric compound that is practically found everywhere on Earth and is essential for the sustainment of human life. Water is a universal solvent, thus various contaminants can be dissolved into it, rendering it unsafe for human consumption. The significance of environmental sustainability in terms of humans' health and the preservation of ecosystems is well documented. Specifically, United Nations have set 17 Sustainable Development Goals designed to be a blueprint to achieve a better and more sustainable future for all. Our study is centered on goal number 6, namely clean water and sanitation. Indigo carmine is an organic salt that is soluble in water, and its main mode of production is the sulfonation of natural indigo. Indigo carmine is an approved colorant that is mainly used in food, cosmetic, clothing, and pharmaceutical industries. Especially as a food colorant, it is used in ice creams, sweets, baked goods, flavored drinks, sauces, and chewing gums, with its maximum permitted levels set by the European Union and the United States vary between 50 and 500 milligrams per kilogram of food. Although it is an approved colorant, it has been linked with a variety of severe effects on human health, such as hypertension, cardiovascular and respiratory effects, carcinogenesis, and neurotoxicity. Therefore, treatment for the removal of indigo carmine from the aquatic environment is considered necessary, and various methods have been already applied, including adsorption, electrocoagulation, chemical oxidation, bacterial treatment, membrane filtration. Especially adsorption, chemical oxidation, and membrane filtration are considered to be the most effective methods for the purification of indigo carmine contaminated waters. Our team has already studied the removal of indigo carmine from the aquatic environment via adsorption onto hitosan and hitosan beta cyclodextrin beads and hitosan cerium and hitosan beta cyclodextrin cerium granules, and some promising results have emerged. The efficiency of hitosan and hitosan beta cyclodextrin beads was 90.45 and 94.47% respectively. Optimum values of pH and temperature were found equal to 4 and 25 degrees Celsius respectively, with the adsorption dosage varying between 100 and 1000 milligrams per liter. On the other hand, the efficiency of hitosan cerium and hitosan beta cyclodextrin cerium granules was 90.46 and 92.34% respectively, with optimum values of pH and temperature being 3 and 50 degrees Celsius and the adsorbent dosage varying between 100 and 500 milligrams per liter. Manganese oxides are ubiquitous materials that can be found in nature and are utilized in various ways in the water treatment. Their application in the drinking water treatment is mainly for the adsorption of various contaminants and the oxidation of inorganic or organic contaminants. Manganese oxides and manganese oxide-based materials have been efficiently utilized in dyes, metal ions, and metalloids adsorption. Furthermore, the efficiency of manganese oxides in the oxidation of inorganic and organic contaminants has revealed promising results. The oxidizing properties of manganese oxides are attributed to its ability to form various oxides with different oxidation states. In particular, delta manganese dioxide is commonly found in soils and presents a high reduction potential equal to 1.23 volts. Thus, a growing interest towards the study of water purification by means of delta manganese dioxide treatment is documented. Delta manganese dioxide especially has been found to oxidize both phenolic and anilinic compounds, with the rate limiting step of the reaction being the electron transfer or the precursor complex formation. The reaction mechanism between phenolic compounds and manganese oxides consists of a series of one electron transfers, resulting in the formation of phenoxy radicals, which subsequently can either undergo further one electron transfer forming benzoquinone-like compounds or dissolve from the reactive side of the manganese oxide, followed by the coupling and formation of polymeric products. The first reaction pathway is occurring as a result of electron transfer being the rate-limiting step, while the latter because of precursor complex formation being the rate-limiting step of the process. Absorption of water contaminants is of greater extent if the electron transfer is the rate-limiting step, whereas oxidation of water contaminants is of greater extent if the complex formation is the rate-limiting step. Our team has studied the simultaneous oxidation and absorption of acetaminophen from the aquatic environment using delta manganese dioxides. Our result depicted that delta manganese dioxide was in fact able to completely remove acetaminophen in concentration between 25 and 100 milligrams per liter, and the optimum pH values and temperature were found equal to 3 and 50 degrees Celsius, respectively, with delta manganese dioxide dosage in the range of 100 to 800 milligrams per liter. The main scope of the present research was to assess the ability of delta manganese dioxide to purify waters contaminated with indigo carmine. Moreover, we conducted an in-depth analysis on the effect of the operating conditions, namely pH, indigo carmine concentration, delta manganese dioxide concentration, and temperature in the process. We studied the effect of pH, initial indigo carmine concentration, initial delta manganese dioxide concentration, and temperature towards the removal of indigo carmine by changing the value of each parameter while maintaining the values of all other parameters constant. The values in blue color here indicate the constant value of every parameter when investigating the effect of another parameter. Furthermore, we will present you our results regarding the kinetic and thermodynamic analysis. We calculated the removal of indigo carmine by delta manganese dioxide at any time interval by the equation presented here, and indigo carmine concentration was determined spectrophotometrically at 610 nanometers. The evaluation of kinetic parameters was based on the model proposed by Zhang and his co-workers. The aforementioned model is based on the formation of a precursor complex between the surface of delta manganese dioxide and the organic reductant, in our case indigo carmine, followed by an electron transfer within the precursor complex, resulting in the generation of organic radical species and the redox of delta manganese dioxide. The rate-limiting step of the reaction between indigo carmine and delta manganese dioxide can be either the precursor complex formation or the electron transfer. In the first case, longer reaction times are required and polymeric compounds are expected to be formed, whereas in the latter case, fast removal of indigo carmine by sorption onto the surface of delta manganese dioxide is expected to occur. When the precursor complex formation is the rate-limiting step, the model is expressed by the first equation. When the electron transfer is the rate-limiting step, the model is expressed by the second equation. The data from all experiments were fitted in the proposed models for both rate-limiting steps using sigma plot. The effect of pH on indigo carmine removal by delta manganese dioxide was investigated at 4 different pH values. According to the presented result, pH is shown to have a strong impact on the removal of indigo carmine by delta manganese dioxide. Indigo carmine removal increased with a decrease in pH, and at pH equal to 3 was almost completely removed within 2 hours. A considerable removal of indigo carmine was also observed at pH equal to 3.5. However, at higher pH values, the concentration of indigo carmine did not change significantly over time. The significant decrease of indigo carmine's removal with increasing pH can be attributed to its adsorption to the surface of the oxide being more favorable at low pH values and to a decrease in the redox potential of delta manganese dioxide with increasing pH. Additionally, zeta potential of delta manganese dioxide has been observed to decrease with increasing pH, thus the adsorption of indigo carmine in its surface become less favorable. The effect of indigo carmine's initial concentration on its removal by delta manganese dioxide was investigated at 4 different initial concentrations of indigo carmine. Complete removal of indigo carmine is achieved only at an initial concentration of 50 milligrams per liter. However, it is worth noting that for the other studied values of the indigo carmine concentration, a significant percentage of it is removed within 3 hours. In general, at all studied concentrations, removal of indigo carmine is exponential, with a plateau at 90 minutes for initial indigo carmine concentration equal to 100 milligrams per liter, and at 2 hours for initial indigo carmine concentration of 150 and 200 milligrams per liter. This is attributed to the high concentration of indigo carmine which was studied, resulting in the oxidation of large amounts of its molecules by delta manganese dioxide, resulting in the formation of free radical molecules of indigo carmine at a greater extent, thus accelerating the overall process. The effect of delta manganese dioxide's initial concentration of indigo carmine's removal was investigated at 5 different initial concentrations of delta manganese dioxide. Complete removal of indigo carmine was achieved within 90 minutes for a delta manganese dioxide dosage equal to 800 milligrams per liter and within 2 hours for 400 milligrams per liter. A further reduction in the initial concentration of delta manganese dioxide results in a decrease in the removal of indigo carmine. In addition, a more abrupt decrease in indigo carmine's concentration was observed with an increase in delta manganese dioxide concentration. The requirement for high initial concentrations of manganese dioxide for the rapid and complete removal of indigo carmine suggests that in low concentration of delta manganese dioxide, a saturation occurs between it and indigo carmine. The effect of temperature on indigo carmine's removal by delta manganese dioxide was investigated at 4 different temperatures. Complete removal of indigo carmine is not achieved at any studied temperature. However, an increase in temperature resulted in an increase in the efficiency of the process. In addition, with increasing temperature, a sharper decrease in the concentration of indigo carmine was observed during the early stages of the reaction and suggests that some form of chemisorption occurs through the formation of a chemical bond between indigo carmine and delta manganese dioxide. Data from all experiments were fed to the studied kinetic models, with the parameters of each model and the coefficients of determination being presented here. Both kinetic models were a good fit for the kinetic data and provided satisfactory values concerning the coefficients of determination, thus indicating that the reaction between indigo carmine and delta manganese dioxide may be explained by a combination of both models. However, in the vast majority of our experiments, the model that assumes the electron transfer to be the rate limiting step exhibited higher values of coefficient of determination, whereas the model that assumes the complex formation as the rate limiting step exhibited higher values of coefficient of determination for the experiments that were conducted at pH equal or greater than 3.5. Based on the aforementioned results, it can be noted that in strong acidic conditions, the reaction between delta manganese dioxide and indigo carmine is governed by the electron transfer. For both models, an increase in the initial concentration of indigo carmine in delta manganese dioxide and an increase in temperature or a decrease in the pH values resulted in a respective increase in the rate constants of each model. Thus, it can be stated that the reaction between indigo carmine and delta manganese dioxide occurs more rapidly at high initial concentrations of indigo carmine and delta manganese dioxide, high temperatures, and at low pH values. Concerning the model that assumes the electron transfer as the rate limiting step, the total reactive surface sites that oxidize the parent indigo carmine molecule remained relatively stable by changing the initial concentration of delta manganese dioxide and temperature, while they increased by increasing the initial concentration of indigo carmine and decreased by increasing the pH. On the other hand, for the model that assumes the complex formation as the rate limiting step, the total reactive surface sites that oxidize the parent indigo carmine molecule increased by increasing the initial concentration of indigo carmine and decreased by increasing the initial concentration of delta manganese dioxide, the temperature, and the pH. Concluding, the presented reduction in the total reactive surface sites with an increase in pH for both models indicated that the reaction between indigo carmine and delta manganese dioxide is favored at strong acidic conditions. Based on the Arrhenius equation, the activation energy was calculated equal to approximately 21 kJ per mole. Thus, reaction is endothermic, and an increase in temperature will lead to an increase in the reaction rate between indigo carmine and manganese dioxide. Additionally, the value of the activation energy suggests that the reaction between indigo carmine and delta manganese dioxide is subject to a sorption mechanism by the formation of chemical bonds between indigo carmine and manganese dioxide. To conclude with our work, delta manganese dioxide exhibited high efficiency towards the removal of indigo carmine from aqueous solutions. Moreover, removal of indigo carmine was found to occur more rapidly at high indigo carmine's initial concentration, using high delta manganese dioxide's initial concentration at high temperatures and low pH values. In strong acidic conditions, the reaction between indigo carmine and delta manganese dioxide is governed by the electron transfer, while at pH equal or greater than 3.5, the complex formation is the rate-limiting step of the process. Thermodynamic analysis of the process indicated that the reaction between indigo carmine and delta manganese dioxide is endothermic, and an increase in temperature will result in increased reaction rates. To sum up, delta manganese dioxide is a viable solution for the removal of indigo carmine from the aquatic environment. Regarding some future prospects that can be derived from our research, delta manganese dioxide should be incorporated into the drinking water treatment plants as a chemical water decontamination agent due to its high efficiency. Moreover, the coupling of delta manganese dioxide with ketone-based adsorbents, resulting in the formation of innovative functional materials, could be an effective tool for water decontamination. Additionally, a novel process for water purification can be designed by fabricating distillation columns packed with delta manganese dioxide. Finally, the demand for acidic conditions for delta manganese dioxide to be at most effective can cause some concerns, since the pH of drinking water varies between 6.5 and 8.5. However, the addition of neutralizing solutions, such as sodium carbonate, after the decontamination process can adjust the pH to the desired value. Thank you very much for your attention.